So my talk will be aimed at those of you who have a vague idea of what an operand is. So I apologize to all those who have a very good idea of what an operand is, because it may be a bit slow and boring. So, for the time being, I will work in, I will talk about operads in topological spaces with a Cartesian product, or even in sets with a Cartesian product. Of course, every operand in sets can be viewed as an operand in topological space with a discrete topology. And so I remind you from Bruno's talk that if P is an operand, then there is a notion of P algebra. P algebra is a space A together with action maps like this. And you can think of P a little bit as a ring and A as a module. So if you have a map of operands, P to Q, well, let's say Q to P, a map, then every P operand, P algebra, is a Q algebra. You can just restrict the structure along phi, right? So that's one. So it's a nice framework to compare various kinds of algebraic structures. And the other thing is that something which will come later. The framework is also very suitable for moving from one category like top to another along a sufficiently monoidal functor. So you can move like homology, which goes into graded vector spaces, for example. So we also saw something about this when we compared the little disks operand to the Gerstenhaber, the operand governing Gerstenhaber algebra structures. Okay, so if you have, also to simplify the situation a bit for the time being, I will talk about non-symmetric operands. These symmetries usually cause a lot of trouble, especially notationally. So for the time being, operand means non-sigma operand. There's a bit of a strange tradition in the area, of course, to have the unmarked case to be the one with the richer properties, but unmarked in the linguistic sense of the word. Okay, so let's go back to the second line. So a P algebra is a space together with some action maps, alpha n, for example, and they should satisfy some equations, of course. So a P algebra, the maps have a star giving the P algebra structure should satisfy equations. such as what you could do, for example, is you could have an operation of p entries, of m entries, p of m entries, and on the ith entry you could compose it with an operation taking n variables. So then you could apply p circle iq to a1 a n plus m minus 1. Maybe I should write m plus n. What am I doing?
Capital Q is capital P, right?
Sorry?
Capital Q is capital P.
Yeah, why not? Thank you. I wanted to be this. This should be the same as applying p to a1 up to ai minus 1. Then you insert the result of applying q to n variables, so that goes up to ai plus n minus 1. And then the rest of the a's, m plus n minus 1. Okay, so this is sort of the associativity condition of this operation. There's also a unit, so I of a is always a. I in P1, the unit. So you could ask yourself, what if these equations don't hold at all? Or what if they only do hold up to homotopy? So the first question is a bit easier to answer than the second, and is related to forgetting that P is an operad, just keeping the sets or spaces P of n and constructing the free operad associated to it. So if we just have, I'm writing in the dark I think, but I already started. If we just have the alpha n without equations, this structure is controlled by another operad the free operad on the sequence P of n and bigger than or equal to 0, right? So I call this operad free of P. So let's describe what it is. So it's very easy to see what it is. Free P of n, the elements here are things to which you can are operations given by successively applying p's, but not little p's, but not putting any equations. So these are, so has elements given by planar trees, whose vertices are labeled by elements of the Pn. So I will be a bit more precise. So there will be lots of trees in this talk. So when I say tree, it can be planar or not, but when obviously I've written planar, it will always be finite and it will be rooted. So there will be a root. So this means finite, rooted, and with leaves. So the various ways to formalize this, but I will draw a picture. So, excuse me. For example, this is a tree which has a root, which I will always draw on the bottom. And it will have leaves, 1, 2, 3, 4 leaves. So there are some sort of external edges of which I select one, which I call the root, and that gives me an orientation in the tree.
So what would be a tree that is not planar?
I cannot draw it. Well, I can draw the set of planar structures on a non-planar tree, if that's what you want me to do.
So for the moment, Pn is any collection of spaces.
Yeah. And so then you label these vertices. So this one you have to label by an element of P3. This one you have to label by an element of P2, sorry. P3, P double, and P2 again. And this one should also have a label P0.
No. Okay.
Can be constants in the theory, so to speak. I don't, emphasize this, but we talked about the associative operand, for example, which has describes the unit of the monoid by an element of P0. Okay, and these structures, a set of these structures. So you could write a formula: 3p n is a sum over all such T, or more precisely isomorphism classes of planar trees, and then the product for all vertices in T of P of the number of inputs of that vertex. Okay, this is the formula. Good. And the collection of the 3p n for various n is again an operand, because you can, if you have, this is an element, this represents an element in 3p. Now I have to count 1, 2, 3, 4. If you have 4 other such trees, you can stack the first tree here, the second one here, the third one here, fourth one here. It's called grafting. So it has an operand structure by grafting. So 3p has the structure of an operand. Again, non-sigma, where substitution or composition, I forgot the name that you used. Sorry? Did you call it substitution or composition?
Substitution is the monad structure, so this is really correct.
Yeah, but where composition,
Composition
it's just a question about the terminology, is given by grafting. Okay? So you could even do this for the operand. So this is a sort of minimal example where P is associative operand, viewed as a non-sigma operand. It has just a point for every n. So these labels don't mean anything. It's the same label all the time, so to speak, except that it remembers the arity. And then you get the operand of planar trees. That's also an operand. That is perhaps the mother of all operands. At least if you go back to Stashev rather than to loop spaces. Okay, let me create some space. So trees themselves form operands, and labeled trees also form operands. That's an important thing to remember. So if you started with an operand P in sets, you get another operand in sets. And if P has a topology, you can of course drag the topology along and put an obvious topology here. You get another nice topological operand. Okay, I forgot all the relations that existed in P. This is a little bit uncommon because there's sort of one trivial relation for the unit which you could keep. Okay. So there is, if you view P not just as the collection Pn, but also remember I in P of 1, which should act as the unit, there is a relative free construction free, let me write it, sub I of P, and the elements are now elements of free Pn, free IPn, are equivalence classes of label trees where if you have an edge labeled by the unit, so if somewhere in the tree there is, denoted I, sorry, there is a situation looks like this, then this is equivalent to, let me not make them all ternary, just this. So you can erase vertices labeled by the unit, which forces them to act, because of grafting, this forces them to act as the unit. You have to think a little bit what it means if there is no vertex here. This could be the root. Okay, you could still erase the unit. So I hope this is clear. Maybe I'll write. So these are local pictures.
Should be the same amount.
Sorry?
So the valency should be the same.
Well, yeah, that's a very good suggestion. I thought it was very good because when I draw a tree, it's always binary for some reason. So I deviated from this, but too liberally. Overcompensation, yes. Good. Okay, so there are obvious quotient maps. So there are maps of operads. Free P, free IP, P. So maybe P. I think I will call both of these epsilon, although I probably will not talk very much about this one. Okay, so if you have a tree, let's go back to the first picture. If you have a tree, and you already knew that P were an operad, then you could compose. You could take P circle 2 P primed, P prime circle 3 P double, and so on. You could contract the whole tree by using the composition in the operad. That's this map epsilon. And if you pull back the algebra structures, every P algebra, here you have a P algebra structure. Here you just remember that the unit acts as the identity, and here you just remember the action maps and have no equations. Okay. So now I want to move to the situation where these equations, instead of not holding at all, hold up to homotopy. So there will be an intermediate operad here, W maybe sub I of P. And this will controls the equations up to homotopy. I'm hesitating whether to insert a word here, but let me just say it. It's not just saying that there exist homotopies, but these homotopies are given by the algebraic structure and they are coherent, as the word is. So W sub I of P is what is called the Boardman-Vogt resolution of P. And it's a resolution because this will be, if you fix n, so this is an operand, and for a fixed n, this will be a homotopy equivalence. And it's not quite free, but it's certainly much more free than P itself. It sits in between. And you can do this construction in various other contexts as well, so it's a little like quasi-free. Yeah? If you would forget, I'm going to put some topology, even if P is discrete, and if you would forget this topology, it will be free. So it's like forgetting the differential and then something is free. So the elements of W, I may forget this I later on, but that will just be a mistake then, are equivalence classes of planar trees. Like before, but in addition, but with an additional labeling of the inner edges by a length. I will try to use Greek letters for the lengths, alpha is 0, 1. Okay, so let me draw the example that I just erased. If you still have it on paper, that might help. Something like this. P, Q, R, S. So there are leaves, and there are internal edges. Internal edges run between vertices, and I'm going to give these a length. Alpha, beta, gamma. Okay? And now there are two equivalence relations. Two relations. Edges of length 1, of length 0, sorry, can be contracted. So I will draw a picture maybe. So local picture, if you have a P here, a 0 here, and a Q here, then this is equivalent to this is now P circle 2Q, right? That's one relation. And I'll put the next one to the side of it. And the second relation is again has to do with this unit. I could use the pictures here, but what do we do if there are lengths here? Okay. So for units, I, alpha, beta, gamma, I again erase the vertex and I take the maximum of the lengths. Well, I will make a comment on about this in a minute. Okay. And if one of these becomes external by erasing this vertex, you forget the length because there's no length on external edges. So let me also write a picture for this. I alpha is equivalent to Okay? Let me emphasize that these are local pictures. Okay? There could be lots of other things happening in the tree here. Now, so now there is a lots of topology involved. Do I still have this formula? No. Because if you fix the tree, there is a cube coming in, the cube of the dimension of the number of internal edges or inner edges, and there is a topology of the operand coming in, if there is one. Okay?
Also, you didn't say how to compose, right? If you
Right,
compose, you introduce a new internal.
Right. I will. And because of these equivalence relations, you have to put some quotient topology. Okay. So now we can still compose using grafting, and new inner edges will arise, as some of you noticed already, and others knew already. And these new inner edges will get length 1. Okay. So composition. Given by grafting, giving the newly arising inner edges length 1.
Right, so it's a bit easier to just say that all non-internals are labeled 1.
Yes, you were anticipating my next sentence, because I was about to say that another convention is to give all external edges length 1.
And the bottom edge is considered as external.
Right. Good. So now you ask me why the max and not something else. So I need this composition to be compatible with the equivalence relation. Okay? And there I use that 0. So maybe I'll write these conditions. So everything is well defined. Because maximum of 0 and alpha is alpha, and maximum of 1 alpha is 1. And the same in the other variable, but it doesn't have to be symmetric. Okay, so you could use any operation which satisfies these conditions and the flips. Yeah? So 0 acts as a neutral element and 1 as some sort of absorbing element. So you could also do flip the interval around and then do multiplication, for example. 1 minus alpha, alpha 1 minus beta. Okay. So in this operand, for example, if you have two operations P and Q in the old operand P, let's take them both binary. You get a whole segment of operations in the new operand. Okay? And for t equals 1, so in W of P, for t equals 1, this is the composition. And for t equals 0, this is some operation from P again. P circle 1 Q. Yeah? And T parameterizes a homotopy from the free composition to the old composition. So if you have an algebra for WP, then the old equations will hold up to homotopy. Okay?
Is there another way to write down that equations hold up to homotopy, or is this also the definition?
This is one way to define a coherent homotopy because of all these trees and so on. All the coherences are put in.
Is there a general way, if I gave you a set of equations, could you tell me, so I could even give you like a graph, and I want this composed with that. to be the identity? Is there a general way, if I gave you that you could define what holds up to homotopy?
Well, this construction certainly makes sense for much more general structures than just these rooted trees. So, with your example of the graph, I suppose the answer is yes. And there is also a notion of coherent diagram of spaces, for example, a very classical notion in homotopy theory, which can be done in exactly can be described in exactly the same way. So. Okay, so a WP algebra, maybe I can say something about these coherent diagrams in a minute. So WP algebra is it's like a P algebra. So the relations, the equations hold only up to homotopy. So I could say something about these coherent diagrams if there is time at the end. Good pretext to talk a bit about colored operands. So I would like to look at an example just to relate this to a much more classical notion. So example, so sort of a minimal example again. P is the associative operand, but now I will take out the unit because otherwise there are too many trees. But controlling associative multiplications, but without unit for the moment. So I will take S of 0 to be the empty set. Okay? So let's look at the trees. Okay, so there's only one tree with one leaf. Yeah? So W of S of 1 is a single point. W of S of 2 is again a single point. It's just this tree. Okay? If you would do a symmetric case, there would be two trees. You could label as 1, 2 or 2, 1. Okay. So it's not very interesting so far. WS of 3, now there are this is the chocolate bricks. There are 3 trees. So there is a tree which looks like this. There is a tree that looks like this. Okay, and if I let this interval run in this direction, so this is length 1. If it has length 0, I end up at this tree. Right? I contracted the edge, and I can expand the edge again in the other direction. So I get a subdivided interval. Yeah? So WS of 3 is an interval. So it's not a direct homotopy. But this is combinatorially relevant sometimes. It's not a direct homotopy from the one from A times BC to AB times C, but it's sort of a subdivided homotopy. You put something in the middle and you run in 2 directions.
And there is one parameter. No, in the middle, no parameter.
No.
It's to extreme one parameter.
Yeah.
One inner
Yeah.
edge.
Yeah, one inner edge. So now let's look at WS of 4. So now it gets a bit more complicated. I'm not sure whether I will get it right. But we will get a subdivided pentagon. Okay? So let me try to draw part of it. Let me first do the sort of classical pentagon because that's easy to remember. You move all the parentheses from right to left. So this could be A, B, C, D, and this could be A, B, C, D, and this would be A, B, C, D, and this would be A, B, C, D. Okay, I could also draw them as trees. So at this vertex I would have the tree A, and then B, C, D. And here I would have D, B, C, A. And I could put something in the middle here where I contract, let me also put this tree here, so this is A, B, C, D. So along these edges I will have a situation like this. Yeah? So let's see, it's not so easy close to the board, but how do I get from here to here? Wait a minute. Yeah, so I contract this edge. Sorry?
You keep the top binary and you do.
Wait a minute, I did that? No, yeah. Okay? So this is the tree A, B, C, D. Okay? And there's also the tree, the corolla here, like this. So this is a square corresponding to a tree with two inner edges, and there are extremities. Wait a minute.
No, you shouldn't do this.
Squares look like this. Okay. Here is a tree with two inner edges. So it's parameterized by this square, two-dimensional cube. And if you contract one inner edge, you get to the boundary. If you contract two of them, you get to the center. Okay. So here is another one. I could draw the other one in the middle, except that I'm too close to the board. So that's BCD. This is like this. Okay, so it's obtained from this one by contracting this one, and it's obtained from this one by contracting this one. So you get a subdivided cubical subdivision of the pentagon, which is the next Stashev polytope. So what this is a subdivision of the Stashev polytope K3 or K2, depending on how you count. This is the subdivision of the next Stashev polytope, and so on. And it continues this way. So W of S of N is a subdivision of the Stashev polytope. Now this construction is in the book that was mentioned before certainly by in the first lecture by John.
The Stashev polytope of dimension n-2.
Yeah. Well, there are two ways of numbering the Stashev polytope.
I
So
say the dimension.
yeah, dimension or variables.
Oh.
So C, Boardman-Vogt, homotopy, invariant algebraic structures. The title is a bit longer. It's in topology or all topological spaces, I don't remember. From 1974, I think. Let me check. I think I wrote it down somewhere. '73. May lead to a question otherwise. So why is it called homotopy invariant? Yeah? So let's see how we can, if we have a WP structure like a WS structure, how we can move it around. So look at the map of spaces. I have X. Okay? Now, these are like these endomorphism operands that we now consider, but now in topology. So if you have a map from Y into Y, you can compose it with F, and you get to X. And if you have a map from Y into X, if you have a map from X into X, you can compose it with F to the N. Okay. So if you would have a WP structure on X, there would be a map like this, WP of N here. Okay? So you could compose, and then you would try to lift here. Yeah? And you would try to lift in such a way that this will again be an algebra structure, a P-algebra structure. So how can you possibly do that? So you do it, you find the lift. So try to find the lift by induction on the size of the tree. Yeah. So if you suppose you've done it for smaller trees, then if there is a length, and you have a tree with n leaves, if there is a length 0 occurring somewhere, you already know what to do, because you can contract this edge and you arrive at a smaller tree. If there is a length 1 occurring somewhere, then you know for this thing ever to be an operand map, you have to take the composition, okay, of two smaller trees. So if there is a length 0 or length 1 anywhere on an internal edge, you know what to do. So you know what to do on the boundary of the cube corresponding to a tree. Yeah? So you will be able to lift if this is what is called a trivial fibration. So I forgot which color was visible. So if one of the internal edges has length 0 or 1, we know what to do.
How do you decide how to lift Corollas?
Sorry?
How do you decide how to lift Corollas? Smallest graph.
you choose.
Is it always
It's just a point. Yeah, well, for this lift, I have to put a condition, okay? And it will involve the corollas. So, so we know what it is on the boundary of the cube. And for the zero-dimensional cube, the boundary is empty, so that is included as the case dimension 0. What to do? So, we need to lift. Let me write the map again. So k is the number of internal edges in the tree. We need to lift like this. So when is this possible? Well, topologists know exactly when this is possible. This is possible when this map is a trivial fibration. Yeah? So it needs to be a serif fibration and a homotopy equivalence. You can assume at the outset that it's a homotopy equivalence because I'm discussing when these algebraic structures are invariant under homotopy. Okay? Yes? Thank you. So this can be done when f lower star is a trivial fibration. A serif fibration, as well as a homotopy equivalence, weak homotopy equivalence. And this, in turn, is a condition on the map F and possibly on the spaces Y and X. And in this case, it means that the original map needs to be a trivial fibration and Y needs to be a CW complex. Okay? This is okay. If F is a trivial fibration and Y is a CW complex. So under these conditions, we can lift a WP algebra structure from X to Y, even if we couldn't lift the P algebra structure.
So F is not only a serif fibration, but also a homotopy equivalence.
Yeah. So I'm asking, to what extent are these WP algebra structures invariant under homotopy equivalence? That's sort of the original Boardman-Vogt question. So let's assume that we know already that F is a homotopy equivalence or a weak homotopy equivalence. What other conditions do we need? So to go against F, you need that it's a trivial fibration and Y is a CW complex. So you can play the same game with a very similar diagram to try and push a WP algebra structure down. Okay? So there are similar.
Homotopy coherences between all these choices.
That comes from the induction on the trees and having taken into account length 0 and so on. Oh. Okay. So.
Is there a name for the set of equations you'd have to check?
Sorry? I didn't hear you.
Is there a name for the kinds of conditions you would have to check, or a way of going about writing down all the things you'd have to check?
All the trees, I don't know. So there is a similar condition for pushing down algebraic WP algebra structures from on Y, let's say, on Y the ones on X. Okay? And you can combine these things, and combining these two, the arguments are exactly like those. Combining these, one is able to move WP algebra structures back and forth if F is a homotopy equivalence between CW complexes. So that's the, has been a quick summary of the book of Boardman-Vogt in some sense. Okay, you have the resolution. Of course, it's written essentially before the definition of operand. So the notation is very awkward and it's not so easy to read. But the main point is this construction of this resolution and the invariance of the being able to move WP structures from one place to the other.
Is the construction only for operas or for props also?
I suppose for props too, yeah. But, sorry?
You will have wheels.
Yeah, but what do you call these things?
Wheeled props.
Wheeled props, yeah.
They have only props freely generated by an operand. So they have operand and take all the horizontal concatenation of operations. This is the kind of prop they have. So actually they are working with operand without knowing it. That's right. Half props.
Yeah, but, okay, but there,
No, operand. Yeah.
I mean, you can do this construction of graphs with lengths in a much more general context, but whether it has good homotopic theoretic properties depends on other things that I haven't discussed, namely, to what extent is there a model structure on operads or generalizations of operads and on the associated algebras and so on. So maybe, my time is almost up. So, maybe let me say a few words about other contexts. So I've only used this. I used some closure properties of the category, of course. I took the sums and products and so on, and I used this interval. Yeah. So notice that what we used about top is various limits and co-limits and limits, and 0, 1 with its maximum and its two endpoints with the equations. Yeah. So I will write the equations again. Max 0 alpha is alpha max 1 alpha is 1. Okay. And let me also write this. So if you have any such situation, you could try to do this construction. For example, you could do it in simplicial sets or simplicial objects in some category. Yeah? And so we could also do it for operads in simplicial sets with delta 1 as the interval, representable interval. Okay, and strangely enough, or strikingly enough, I get back 15 years further than 1973 because you get exactly the Godemar resolution. I will maybe say what I mean. You see, if you have an operad P, let's start with an operad in sets. Okay? You could take the free operand. So this is 1958. But you could do it again. Okay? And you could take free of epsilon, or you can take the new epsilon for the free operand on P. This is hardly legible, but I hope you know what I mean. And so on. And you build up a simplicial operand. And if you take the geometric realization of the simplicial operand, you tumble on the old Boardman-Vogt construction. So maybe
But you get something equivalent to the W?
yeah, identical,
Identical.
isomorphic. I don't know whether folk knew this, but so maybe without going into the details, but sort of anticipating maybe a discussion of Koszul, you can also do it in chain complexes. Yeah? You can use normalized chains on delta 1. So you have the length 0 and 1, but length 0 you don't really need because you can always contract the tree, and there is some sort of generic length for this interval, 1 degree higher. Okay, and then then this gives something isomorphic to the bar-cobar, maybe cobar-bar resolution of an operand P. So maybe I told you these operands are a little like rings, okay, or associative algebras. So you could take the free co-algebra. You could forget the algebra structure, take the free co-algebra. Then the old multiplication will act as a differential. Yeah? So that's called the bar of P. So this is the free co-operand on P with the old operand structure of P reappearing as a differential. And if P already had a differential, then you just take the total of these two differentials. And then you could do this again. So you could take cobar. So this is omega B of P in a more common notation. Okay, so this is now the free operand, which we understand well, on bar of P, with a co-multiplication, co-composition maybe, reappearing as a differential. Okay, and this is also a resolution. This is a quasi-isomorphism. And it's, again, literally the Boardman-Vogt. But it's big, okay? So the whole idea of this Koszul resolution is to find something smaller if you know more about P. And this is what will be heavily discussed in the next few weeks. Maybe just to give you a little bit of an idea why this is true. You see, because it's not as complicated as it seems. To take the free cooperand or the free operand, both are constructed using trees. In one way you have composition of trees, the other way of decomposition of trees. So this is some sort of tree. Things here are trees of trees with vertices labeled by P. But a tree of trees is the same thing as a tree with a length, or a tree with two edges of two colors. Yeah? And this is where the delta 1, the generic length of delta 1 and the length 1 appear. And that's how you actually get the isomorphism. Okay, so there are various things I did not discuss. So one thing I did not discuss is when can you strictify or rectify a P-algebra structure up to a homotopy to a true P-algebra structure. That's also part of the game. And if P, in topology, if P is sufficiently nice, you can always do that. Yeah? And the other thing that I did not discuss is sort of a unifying framework to do all these things at once, which is talking about operads and algebras for an operad in what is called a monoidal model category. A general category where you have a nice homotopy theory and you have a tensor product, and these two are compatible. Okay, and that's the best framework, and then you can also try to move from one such monoidal model category to another and prove these resolution theorems and the strictification theorems there. Then the third thing that maybe I will talk about in a couple of weeks or so is there is a slightly more general notion of operad where the algebraic structures have more types. You can have the algebraic structure of a ring together with a module, for example, where both the ring and the module are vary. Or you can have the algebraic structure of a presheaf, where for each object in an index category you have a space, and you have maps between them, a diagram of spaces. So for such colored operads, you can also do this Boardman-Vogt resolution, and this gives you this theory of homotopy coherent diagrams of spaces, for example, and strictification for those. So this we will see later. Thank you.
Any questions? Can you choose your homotopies in WIFP to be compatible?
Sorry?
Given a WIFP, if you have a map from WIFP, your anamorphism operad,
Yes.
can you demand that when you choose those homotopies between the composition freely and the composition in the operad, can you choose those to be compatible so that when you have two different ways of composing to get a bigger operation, and you take that homotopy and you compose it with the guy on the left, and you take a homotopy, compose it with the guy on the right, get a homotopy between those homotopies. Can you choose all of your homotopies compatible?
Are you talking about one space? Or, I'm sorry.
talking about if you have, so WIFP, you have a whole bunch of homotopies.
In W of P,
Yes.
yes?
Can those homotopies always be chosen compatibly? As in, if you had some space that had an action of the WIFP operad, that would mean not that it had an action of the P operad, but that you'd have chosen homotopies between various free compositions and actual compositions.
Yes.
But those homotopies, you could also compose them on the left and the right with other
operations.
and you want to know
yeah.
if those homotopies then that you've
And
chosen.
all these
they-
homotopies are built into the system.
So there's a homotopy.
This is the meaning
there's a
of coherent homotopy.
So these are all,
They're all built in. You see, because I have lots of parameters. Yeah, I have for example, I have a homotopy from, let's take three operations, P, Q, R. Yeah? Unary. Okay? Then this parameterizes a homotopy from P to Q, and this parameterizes a homotopy. This parameterizes a homotopy from The free
Oh, I
composition
know
of
what
P and
you-
Q.
never mind.
Sorry? And then
I
there's the
see what you're
cube,
gonna
which
say.
gives the homotopy between the homotopies, which is parameterized by the pair.
I'm impressed that you can write down all of that stuff and check it. Yeah.
Lots of trees.
Any other comment, question?
Okay, so
Thank you.